Anyway, so the real story I'm going to tell is actually some sort of a revisiting of things which have been known in the community for a number of years. The question is really this sort of vorticity strain alignment in turbulence. Well, as I will be reminding, there are some sort of naive expectations, and in fact, when you sort of look at your hard data, it's, it shows that turbulence has absolutely nothing to do with what you would expect. Well, the way I will do it is, of course, by using my sort of own biases, which some of you sitting in this audience may know already, i.e. I will go Lagrangian, i.e. try to follow things as they move about in the flow. And the other bias will be, instead of looking at the velocity gradient tensor, to sort of expand a little bit the objects I'm looking at, and looking at a bunch of points forming a tetrahedron that are going to be the main objects that I will be looking at. Okay, so the work done has been done with my collaborators in Göttingen, Haitao Xu and Eberhard Budenschatz. Well, the experiments, and so it's a great pleasure for me who has been doing these games on a computer or on a piece of paper for a number of years to see that some of these ideas actually can be seen in the lab, and lots of fun experiments going on. Okay, so the story in a nutshell. So here is our favorite Euler equation returned in terms of the vorticity. Well, pretty. What did you say? Did I say Euler? Yes. Oh, I'm sorry. Euler Navier-Stokes. Right. Sorry. So obviously, just advection, and well, the dissipative term, and of course the one that we all stare at in great detail is the stretching term. So just the product between the strain, i.e. the symmetric part, and omega, well, vorticity. Okay, so so the story that the great people before us started telling was that you can find this argument in Tennekes and Lumley, and so lots of people have talked about it before. Well, imagine that you have some parcel of fluid with some little vorticity at time t equals 0. And superimpose into it some strain, so your thing will be try to stretch, and well, in stretching, so it will tend to, it's a finite, it's a incompressible fluid. So as it gets longer, it also gets thinner. As it gets thinner, and if you sort of look at the same amount of fluid, then of course the moment of inertia in the direction which has been stretched gets lower. And if you invoke conservation of angular momentum, well, then you deduce that omega of t increases. So that's what Tennekes and Lumley say in their book. And of course, if you take this argument a bit literally, well, you would expect that the vorticity will align preferentially with the strongest eigenvalue of the strength. Okay, so that's for the trivial part of the story. Now, of course, well, like many of you, if not all of you know, that's not at all the way it works. In fact, when you look at data, that has been noticed, well, the first real hard evidence came from Ashurst and a number of people back in 1987. In fact, is that vorticity aligns instead, well, doesn't align particularly with the strongest eigenvalue. So here a PDF of the cosine would show something which is essentially flat for the cosine between alpha, between omega and the strongest straining direction, and instead you'd see some sort of a good peak, so showing indeed some alignment rather with the intermediate one, which happens to be positive for lots of reasons. And of course, well, just by conservation, you would have to have a tendency of omega to be perpendicular to the third one. So, and that has been confirmed in various experiments. So it's Arcades, Nover, and collaborators did that in some real flow. Okay, And so, well, this story has a long, well, you know, that's, this kind of question has been looked at by a number of people. Something message out sort of guessed based on his numerics that there was something funny, and you know, lots of people have mentioned this. Okay, so like I said, so that's sort of for the, well, sort of what is known. And so what well, sort of I will take some sort of a side way, and like I said, I will go Lagrangian, i.e. Sort of moves with the flow and see what we can learn from there, and also instead of looking at the velocity gradient, so i.e. sort of really following things, points which are extremely close, I'll do instead finite size objects. Okay, so tetrads, well, sorry, again, so you already know me. So the way it works, well, it's sort of the usual construction is to say, well, if you give yourself 4 points which are not aligned, well, then from them you can, in principle, get a notion of what the velocity of the fluid is. Not only sort of in velocity, of course, which you can say very much about, but more about the velocity gradient. So in a sense, if you points span the whole space, well, then you can sort of get an idea about how you do, you know, well, whether there is a sort of can be traverse, sort of stretch, all these kind of things. So there is a construction, well, basically, so if you have 4 points, you obviously, well, if we assume that we have an homogeneous flow, you don't care about the center of mass, which you readily subtract, and what you do is you introduce a matrix M such that the matrix of this sort of a relative position, URI minus center of mass, is equal to the velocity UI minus again center of mass. So center of mass here is ignored. Okay, and then of course, well, what you did with the velocity gradient tensor, you can do, of course, also for this perceived velocity gradient tensor, so that we point, well, we sort of use this term here to avoid confusion. So it's, you tend to think of it as the velocity gradient tensor as it is perceived by sort of the points around you. And so you can decompose it, of course, in terms of asymmetric and an antisymmetric part. The antisymmetric obviously containing information about vorticity. Okay, so what the data I will be showing is based on, well, sort of experiments. So it's a French washing machine designed in Germany, so it's much better. So that's this kind of apparatus that Edward Bodenschatz and collaborators have, have many of them in their facility in Göttingen. So here these things run at a Reynolds number of between 350 and 815. Well, scanning sort of a very big Reynolds number with an integral scale which is about always a few centimeters, and a ratio between large to small scale which is getting close to 1,000 at R lambda equal to 350. So it goes up, of course, as you increase the Reynolds number. So here, sort of a sketch, some information about the flow. Here, in fact, the measurements are being done here. So in the center of this thing here, where the flow is kind of where the mean flow is not too strong. So in other words, things are not swept by immediately. So you try to sort of find some location where things are as stationary as possible. So, and well, the thing is being arranged so there are roughly 100 particles in the field of view at any time. And well, so of course what they do is that they store tons and tons and tons of image, or rather, well, they process tons and tons of image and record position of all the particles and their velocity, etc. And well, for the game, for what we're trying to do is sort of to find several particles which form whatever shape you want to have. You prescribe whatever shape you want, and so you try to sort of have it to find occurrences of these things. So here it's being done by searching for isotropic tetrads with distance between where the distance between points is within 10% a given distance. Okay, and sort of a rather an impressive DNS, like compared to anyone else here. I should be ashamed of myself. So it's nothing, it's like 400 Q. The sort of, in a sense, the lesson here is that it's good enough to actually check a number of things and to sort of be consistent and to show that, after all, things extrapolate pretty well. Doesn't mean that I will win at this game at all times at some point. I know that there are things where I will have trouble if I don't move up in Reynolds numbers. Okay, so instantaneous alignment. So, of course, like I said, so we have some data, it's been documented how vorticity and the strain align at the level, at the gradient level. Now, of course, sort of the obvious question is what happens when I look not at the sort of a gradient, but at the sort of a perceived velocity gradient tensor, i.e. the things with a finite distance. So typical results are shown here. So, so remember, I was showing the PDF of alignment between omega and the intermediate one, and the lesson was that at very small scale, things were sort of shooting up. So there was some sort of a strong alignment, i.e. a peak of probability where the cosine was 1, i.e. when the two things were almost together. So here, what's happening, so obviously you can read the legend. So the general trend here is that as you decrease in R0, well then, so i.e. if you take objects which are smaller and smaller and smaller, then what you see is that this PDF starts going up. So in other words, what's being said is that you always have this effect which sort of disappears more or less when you sort of come very close to the integral range. However, when you go to sort of the smaller scales, well, you start the thing increasing, and the alignment effect becoming visible. Same thing for the anti-alignment, so the tendency of the omega to be perpendicular to the most compressing direction. So that's this picture here again. So as you increase R0, well, you'll see sort of the peak close to 0 increasing. And so here, to recap, sort of show all sorts of data. So here we have the alignment between sort of the square of EI omega, EI omega squared mean value. So 1/3 would be neutral. And so what you see is that there's not very much happening for E1. It's always close to, to a third, i.e. to sort of a neutral situation. A good alignment of E2, which becomes more prominent as you decrease length. So here length is in abscissa. And so as you decrease it, well, you see it going to some very high value corresponding to dissipative. And so for E3, that's the opposite. And here, possibly, the sort of symbols are for the experiments. Here, you may see here some sort of inertial range where things become universal, i.e. not depend anymore on the particular length you're looking at. Okay, so now the alignment dynamics. So I promised I would do Lagrangian, so let's do Lagrangian. So let's first look at what happens to one of our favorite objects. So here, this white thing here would be an experimental tetra. So that's actually coming from flow measurements. So here you have 1, 2, 3, 4 tracers. And so what I have shown here are the trajectories of these points, in real flow. So that's really by how much they've moved. Actually, it's actually they moved more. So I think we sort of shrunk it here. But anyway, so obviously the things that everybody sees is that there is some deformation. That's sort of obvious. You start with something which is pretty much regular, i.e. all the distances are more or less the same, and here something has happened. Now, obviously, okay, so that one is just to show, okay, so we're trying to make a story that the things sort of moving past by, and so you see something. That's not particularly useful, I guess. What's more interesting, perhaps, is to look at it in some particular reference frame, i.e. the reference frame that diagonalizes the string matrix at the same scale. So E1, E2, and E3 would be the eigenvectors of the strain with lambda 1 greater than lambda 2 greater than lambda 3 being the 3 eigenvalues. Now, what you see immediately, so it's exactly the same picture I was showing before. in this picture, of course, things look much clearer, right? So what you see is that, in fact, this deformation that you were seeing in the previous picture now is is sort of clearly doing what you would have expected to do, i.e. to align with the sort of highest straining. So in other words, straining means that you tend to, the flow would tend to sort of stretch the object most strongly in the one direction, and sure enough, that's where you see the deformation of the tetrad. Now, I've drawn here, without telling what it was, this magenta arrow. That's effectively the vorticity. So that's sort of the rate of rotation here. So at time equals 0, there is no particular alignment with anything. So I'm sort of I told you that it should be rather oriented with this. Here it's not particularly obvious on this picture. Well, actually, maybe there is a bit. Okay, never mind. However, what's becoming clear at a later time is that this thing has certainly aligned a great deal with E1. So
sorry, the vorticity of the center of mass or the coarse grain vorticity?
Or the coarse grain vorticity. Right. No, I don't know the vorticity. I mean, these guys don't know. They can tell you. Right. So they would have to sort of get many more particles just after the four. That's the information that you can get out of it. Nothing more. And so that picture will show you here the evolution of the vorticity vector. Okay, so here the tidbit of information which is useful to notice is the time which it takes. So the time which it takes for vorticity to rotate from sort of its initial arbitrary random initial arbitrary position to this position at the end, in this picture B, is roughly 0.25 T0. So T0 being sort of the usual R0 square of epsilon to 1/3, i.e., what people would call the number of time based on scale R0. Okay, so another way of seeing it would be just sort of look at the PDF of alignment of E1 of 0. So remember, so now I'm sort of looking at how much aligned I am with sort of this strongest axis, this axis of my strongest straining. And sort of I'm plotting the vorticity. And so at various times, 0, 0.2, 0.4, I'm looking at how much alignment I have. So at time equals 0, both with my Coulombic numerics and with experiments, there is effectively nothing. So the thing is almost flat. There is no particular alignment consistent with anything that you would have guessed. Well, that you knew from other information we had already. When you get this 0.2 or even 0.4, you see, again, with some sort of great fair agreement between numerics and experiments, that there is some sort of a good alignment that's happening, and so that this peak, characteristic peak, cosine equal 1, which shows that indeed things have peaked. So same information, plotted slightly differently. So here I'm plotting the alignment, the square of the cosine of E1 of 0 and the omega. So the thing starts again sort of close-ish to 0 to 1/3, sort of shoots up at 0.2 and then starts to decline for everybody. So there's a number of data. Various experiments, numbers, and etc., etc. So that everybody sort of more or less meets on the same curve. Okay, so shape deformation. Okay, so like 7-8 minute run. I've been talking for 19 minutes. So how does the shape deformation proceed? Well, it proceeds more or less as you'd expect. So here, the way to do it, the way you can think of doing the problem is sort of so you have a shape, right? So you have 4 points which give you a shape. So you can define some sort of a fitting ellipsoid which will sort of be some sort of approximate shape. And so this ellipsoid would have various eigenvalues again, and so you can sort of see how the eigenvalues corresponding to the strongest, largest, the intermediate is the smallest eigenvalue, correlate with the eigenvalue of strength. So here I'm showing the strongest eigenvalue that characterize the shape, and its alignment with E1, so the eigenvalue of the strain, the second eigenvalue of strain, and the third one. So clearly what you see is that obviously initially the thing is more or less random, and so then it sort of goes up and then decreases. So the difference here between the experiments and DNS is that DNS mapping are exactly symmetric. So therefore, the slightest amount of asymmetry will immediately say that I'm completely aligned, so I will get a 1. Whereas the experiments are not quite completely aligned because it's so there's a bit of randomness. So it takes a while before the thing is strictly aligned, and sort of then follows the next. But that's sort of the thing that we see. And well, sure enough, it's the same for the second I, E to I2, that corresponds to the intermediate one, and EI3, that's for the third one. So clearly, well, they sort of align the way you would expect. Okay, so maybe I'll skip that one. So that's sort of the limit of our construction. It's something that Luca and collaborators have noticed. So in fact, there is some sort of fair bit of deformation going on of flattening. So if you wait for too long, you'll see things that will be completely squashed. And so that happens in a time of the order of 0.3, 0.4. So that's this right figure. So then you start seeing lots of these guys which were initially sort of properly sampling the flow around them, sort of all of a sudden degenerating and being completely flat, so which is not good for what we're trying to make them say. Okay, so the last one, okay, so I was, these two previous transparency was showing sort of factual information about how the deformation proceeds. The important thing that, well, the thing that is important, if you remember in particular, this argument that I had in my second transparency, is that there is some conservation here. If you look at the angular momentum, which you can do properly by sort of looking at sum of rho I cross U cross Ui, which is in fact well approximated by some moment of inertia tensor times omega, what you see in fact is this. So over a time of the order of 0.2 T0, remember T0 is sort of the characteristic time scale of this exercise. So you see that the moment of inertia, which we call here gamma, curl to this one direction, divided by gamma 1 to 0, gamma 1, 0, so the initial one, is effectively flat. So ultimately it deviates, of course, you don't expect it to be conserved forever and ever. However, you have some sort of a range of time over which not very much happens, and even here, well, it's of course, obviously things are beginning to go bad, but it's only 50% degree, so it's not exactly conserved, but it's a good approximation of being conserved. However, well, in comparison, if you look at the various moment of inertia, so the one corresponding to 1, so in this sort of a thin direction, so that one has gone down a lot compared to the average of these moment of inertia. So you have, in other words, you have a structure which sort of gets very much squashed. However, sort of the moment of inertia tensor in this direction remains pretty well conserved. So in a sense, what I'm trying to say here is that this picture of Tenekes, which I sort of almost dismissed in my first transparency, well, my third transparency, actually is operating here. Not quite the way we were supposed to. Well, people were thinking about it 40 years ago, but at least there is something of it. Okay, so these are sort of a fairly trivial remark. Well, okay, so if you look at from a modeling point of view, so either from the Navier-Stokes, well, Euler system equation, usually Navier-Stokes don't do very much, or restricted Euler dynamics, Tetra model, or whatever. So Charles Meneval wrote a full review article. I think it's not unfair to say that it's sort of based on this construction or various generalization. So if you take any of them, then of course, well, you have an equation like this. So it's essentially of the form vorticity being stretched by the rate of strain tensor, possibly with some reduction of, well, we tend to think of as some reduction of nonlinearity and possibly some damping. So obviously Euler having no reduction of nothing and no damping of any sort. So then, of course, well, it's fairly trivial to write what's happening for this cosine. So, in a sense, we were sort of interested in this cosine of omega with E1, E2, E3. So, just write it like this, so that you introduce this basis here, and you sort of, it's sort of elementary algebra. You just decompose vorticity as, well, the cosine would be Ci, and there is some norm, obviously, so some the cosine is equal to 1, as it should be. And then it doesn't take you long to write this kind of equation. So again, it's just either, well, it just takes the equations that I wrote and sort of do the most naive manipulations. And so if you look at this, at the way these things change at time equals 0, obviously you get this equation, and sort of here I just sort of slavishly wrote down what they are in components. So obviously, if I take these conventions, which everybody's taking, sort of the first largest and the second largest and the third, well, then it's clear that for the C1, obviously lambda 1 is larger than lambda 2, lambda 1 is larger than lambda 3, so therefore all these guys are positive, you tend to align. No surprise. If you look at the third one, well, it's just the opposite. So lambda 3 is smaller than lambda 1, that guy gets negative. Lambda 3 is smaller than lambda 2, same thing. Result, boom, negative. However, if you look at the intermediate one, well, it's not even clear what it's going to do. Because, in fact, that one is negative, this one is positive. So therefore, you have some sort of a compensation. And in fact, you have something which is pretty close to 0. Okay. Take-home message. Well, so there is this alignment between vorticity and stretching, which, by the way, we haven't quite solved the real, $1 million, well, maybe not $1 million, but so the big question as to why they were not aligned, was the alignment is what it is at time equals 0. However, we see that we can see a number of things by sort of moving from Eulerian to Lagrangian. So here, this sort of tetrad dynamics suggests that after all, these good old simple conservation laws that were invented by our great predecessors actually run as a city after all. Well, so yeah, perhaps, well, I think I said it, maybe I should have stressed it more. The characteristic time here is really this one. So in a sense, at least for the alignment of E omega with E1 of 0, that's the time, and well, not 0, the 10th of it, but at least that's the time. And again, which I haven't shown, but which you can sort of easily see, is that this picture which I've shown you is completely consistent with what's happening at small scale. So in all these phenomena, you can show it also at small scales. So that's sort of reference, the acknowledgement, well, so blah, 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 financial support. So my friends who have sort of made a number of very useful remarks. I'll thank you, and
After.
Is there already enough data to begin to ask whether there is a distribution of shapes that is stationary?
The answer, you mean at time, right,
No,
so
a distribution of stationary in time.
Right, so the best available data comes from numerics. So P.K. Young and company ran a massive simulation, and they start seeing that indeed, if you sort of, as you sort of travel within inertial range, provided it's not enough, which you can imagine is costly, you do see something which look stationary.
In the trials or the tetrals?
Both. So
So there is already evidence for that.
Sort of, yeah.
I was actually quite surprised that the invert scale in the experiment is only 7 centimeters, given that the experiment is almost 10 times bigger.
Yeah, but,
right,
okay, so could be lots of things, and so of course you start off with something, but it breaks into lots of things, and there's the blades underneath. So it has no reason to stay that big.
Yes.
So no, well, so it's a 10, it's a small fraction.
Yes.
Also the size of the
So what's your convention, the wave number where the energy spectrum peaks roughly? Is that then 2 pi divided by L?
Yeah, no, it's actually even more silly than that.
1/1.
So we just say epsilon equal u cube over L.
Yeah.
So that's no, so
And that
obviously
L
you
is
should
7 centimeters.
3/2. So
Yeah.
that's what, so which is not quite the proper way of doing it. So there's almost a factor of 2 compared to standard definition. But that's to win in a factor of 2. That's the standard definition.
And it's reasonably isotropic, you think?
Okay. Yes and no. I mean, if you push it hard enough, you end up seeing an isotropic effect. However, for everything that so you see, so in sense that's sort of a wonder of validation. So you take some sort of a ridiculous simulation, and so the things sort of goes together. And so in that sense, so it doesn't seem to be like.
And the fractionality is relatively high, right?
It's not minuscule. I mean, again, you can see. If you look for it, you'll find it.
Okay, one last question.
Yeah, first thing, my first remembrances of tetrad was back in, I believe, in late '98 or so, when Physics of Fluids had to send me the first paper on the subject to referee, and I happened to be on a lake near Kochi, where I was spending the night on a boat. There was a nice moonshine and kind of music.
Don't tell me it's romantic.
That's very favorable for the authors, that the referee in such surrounding will fall in love with the paper, which I did. But just in order to try to say something nasty, I have the feeling that a lot of the things that have been done with tetrads could be done with infinitesimal tetrads, and not necessarily by taking out the tetrads themselves, but by literally going to non-standard analysis with infinitesimal tetrads. There are some instances, you know what non-standard analysis is. It is a resurrection of Leibniz's infinitesimals, which took place around 1960 or so, and which allows you to define correctly what we understand by infinitesimal number and large number and actually work with them. And there are some instances where results can be obtained, if not completely new ones, at least the proofs can be significantly simpler than those one obtains by standard analysis. So now my feeling is that either tetrads can be taken out completely and go into just stupid derivatives, etc., or maybe to infinitesimal tetrads.
I'd be very happy to continue.
I'm not suggesting that one does an experiment.
That's what I was about to say. So so when the project was devised, sort of the notion that one day this thing would be available was very clear in our minds. So this way you can get sort of this correlation function with more than one velocity and try to do something with that. So that was clearly one motivation. However, I'm certainly very open to other things. It's clear that there are things that we may have abused ourselves in a number of ways. So I'm very happy to consider other approach and to continue discussing.
By the way, I do not know if at this moment there is a person who is at the same time a very good specialist of the mathematics of hydrodynamics and who's intimately familiar with non-standard analysis, but people like T.T. or Bardos would know if such a person exists.
Okay,
Okay, let's start on speaker again.